Okay, hi everyone and welcome to our second session here. We're going to be discussing student understandings of properties of linear transformations, and our presenter today is Sarah Sparks from the University of Northern Colorado. If you have any questions for the presenter during the session, please feel free to enter those into the chat at the bottom of the Zoom room screen, and we'll address them at the end of the talk. And so on that note, I'll hand it over to Sarah.
Thanks. Okay, so yes, I'm going to be talking about student understandings of linear transformations. So my motivation to conduct this research was kind of a combination of my experiences as a student in linear algebra and how I felt like I left my first linear algebra course with not a lot of in-depth understanding, a lot of like procedural, how to, do matrix multiplication, those types of things. But then the concepts from linear algebra showed up in other later courses that I wasn't expecting, and kind of changed the way I viewed linear algebra. And then certainly working as a linear algebra instructor and seeing how my own students were understanding linear transformations, and sometimes working on problems in a way that I didn't expect, all kind of led me to be interested in this area of research. And then there was a call from Stuart for more research in student understanding, specifically regarding linear transformations. So I'm going to be talking a bit about pseudostructural conceptions of linear transformations, which is essentially where a student has a conception of linear transformations that kind of prevents them from seeing the underlying meaning and making connections between notation and meaning of these concepts. We know that this can in particular be a problem when students are kind of looking at matrix notation and understanding how that connects to their more geometric understandings of linear transformations. And we also know that it's important that they are able to view a matrix as a transformation, and that there's tasks that can help in doing so. But a lot of the existing research looked at students who were kind of currently in linear algebra courses. And so that kind of led into my research, where I wanted to see, okay, we kind of know what's going on while they're learning about linear transformations. I want to know more about what they're retaining, what their conceptions look like after a linear algebra course. For my research questions were, what conceptualizations do undergraduate students currently have of linear transformations? And then what mathematical reasoning are they implementing when looking at problem solving situations related to linear transformations? So I conducted semi-structured in-depth interviews with 3 participants. This research was conducted in the spring of 2020, so I ended up being a little limited on the number of interviews I was able to conduct before moving online. But these participants were students who had taken linear algebra at least 1 semester prior. So again, looking at students who had already taken it and were now past their linear algebra course. And I used grounded theory to look at the data and see what themes were emerging in terms of their conceptions and their problem solving. So the 3 participants were Perry, Chad, and Summer. Both Perry and Summer were mathematics majors, each taken linear algebra in some different semesters. So Perry had taken linear algebra most recently, Summer had taken it a few semesters prior to that. In these interviews, participants were asked to define what a linear transformation is and give examples and non-examples prior to kind of looking at any tasks. And then the participants were asked to consider several transformations and determine whether or not that transformation was linear, and to give any other information that they could about that transformation. So you can see that they were given some geometric, some algebraic, some matrix, and function representations. And some were linear transformations like the matrix and function here, and then some were not, like this geometric transformation of the letter F. And so again, they were asked to determine, was it a linear transformation? Why did they say that or not say that? And then just kind of talk about it. In analyzing the data, the themes that kind of emerged were using geometric definitions of linear transformation, using formal algebraic definitions of linear transformations, but also informal algebraic proofs where they used something general but didn't conduct a rigorous proof, and then example use where they were using like a specific algebra example or a specific geometric example rather than a general one. So in conducting these interviews, we found that they had very different conceptions of linear transformations. So Perry came in and was able to write down a portion of the definition of linear transformation. And as they were given different examples of transformations to look at, they started modifying their definition. So they originally didn't include 0 needing to be mapped to 0 in their linear transformations, but then once they saw an example of that and remembered that that was something they needed to be careful of, seeing that and then seeing a non-example of it, they added that to their definition. They also, as they were going through, once they realized matrices were linear transformations or made that connection, they started to try to make a matrix representation of each of the transformations. And when they weren't able to do so, again, started using that to change how they were thinking about linear transformations. Summer had taken linear algebra less recently and struggled to recall the specific definition, and so attempted to pull from her statistics background initially, and so eventually was given a definition of linear transformation to work from to answer the other questions. And was able to utilize that definition, especially in geometric examples, to determine whether something was a linear transformation or not, but was unable to apply it to all the algebraic situations, and also did not was having difficulty using general case type structures for showing that something was a linear transformation. Instead would look at a specific example and say, okay, if this example works, then it must be a linear transformation. Jed was able to kind of smoothly transition between different notations of linear transformation, came in and initially was able to give a formal definition of linear transformation, and was able to look at matrices and know what type of transformation that that matrix or that function was representative of. When looking at how they used reasoning in these problem-solving situations, Perry and Summer tended to lean towards example use. So if they were trying to determine whether a function was a linear transformation and they knew that it needed to follow certain properties, they would plug in some values and make sure that it worked for those particular values. Jed generally was able to provide a more general proof, and also was able to give matrices for any geometric representation and talk about what was happening geometrically for any algebraic example. They each talked about, or as they were reasoning through each problem, they each kind of pulled from their previous experiences. So for Perry, that looked like thinking through what they had seen in past courses, but then also what they had seen in previous examples leading up to that point. For Summer, that looked like attempting to use statistics or other algebraic knowledge. And for Jed, that looked like pulling a lot of information from the physics courses in which Jed had applied his linear algebra knowledge, and also the proof skills that he had from taking proof-based courses. So out of these participants, Perry and Summer demonstrated more or conceptions that aligned more with pseudostructural conceptions. So they were able to think of linear transformations as mathematical concepts, but did not necessarily make the connections to underlying meaning, and were not able to smoothly transition between different representations and how they understood each of those representations to all be linear transformations or not linear transformations. Jed's ability to kind of bounce back and forth between representations and give was able to both reason through conceptually why things were linear transformations and using an algebraic, or not an algebraic, a more formal definition of linear transformations demonstrated a structural conception. So again, a lot of what was demonstrated by these students lends itself to the idea that courses that students take after linear algebra impacts how they are viewing linear transformations and their linear algebra concepts. It also seems to be impacting the development of that structural conception. How they interact with the problem-solving aspects also seems to be based on a lot of the other courses that they've taken, in particular, Jed having taken proofs-based courses, whereas Perry and Summer had not taken proofs-based courses, and this was seen in Perry and Summer's example use versus Jed's kind of general proof structure. So the implications of this research, again, with only 3 participants, are mostly currently limited to this university and knowledge towards what conceptions students are leaving their current courses with, and that implication that maybe what we're doing with linear algebra concepts in courses that they take after their linear algebra course are going to matter in terms of the conception that they are leaving the university with, but also making sure that we're providing students experience without applications of linear transformations, whether in their linear algebra class or in their future classes, making sure that those linear algebra connections in future classes are made explicit, and coordinating with other departments. As we saw, a lot of physics courses are using these concepts, and so how can we coordinate with other departments that are going to have courses that use linear algebra concepts, and making sure that we're supporting students in their development of their conception of linear transformations. Looking forward, definitely extended studies with more participants and other majors or types of math majors would be useful in gaining better understanding of students' conceptions of linear transformations, looking at different properties of linear transformations, and looking at the instructional practices that are developing and supporting students in developing a structural conception of linear transformations. What questions do you have? Right. Well, if there are no questions, just want to say thanks for coming.
I want to ask a question, actually. I'm just wondering, what was like interesting or surprising result that you had in this study?
I think it was interesting to me that Well, there were several things that were interesting. I think it was interesting the different approaches the students took to trying to build, if they didn't come in with a solid definition of what linear transformation was, to trying to figure that out and how they were pulling from these other experiences that they'd had. And I think that it was interesting to hear how much linear algebra had been a focus in physics courses, because I, personally had not taken a ton of college level physics courses. And so seeing all those interconnections was very interesting. Other questions? Well, thanks so much.
Perfect. Thank you so much, Sarah. Thank you for sharing that great insight. And if anyone has any questions, they can, of course, email her later if they think of them. I want to share that the next session will begin at noon. So you've got a little bit longer of a break now. And I will paste shortly the links. Okay. Yeah, so if you want to attend any of those, there's your information, and you can go to the conference website for the general schedule. And also don't forget to swing by the Hawks booth where you can win a gift card. So thank you all.
Thank you. I think I'm gonna sign out and come back.
Sounds good.